we took the following simple version of deterministic quicksort, where we choose the first element. By the way, am I audible? Can somebody
Yes,
confirm?
sir. Yes, sir, you are audible, sir.
Okay, 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 good, good, okay. Okay. We choose the first element as the pivot and then partition as usual, and then recursively sort the left and right portions. Okay. So the average case analysis, in the last lecture we saw that it's enough to do average case analysis over all permutations of 1 to n, that is pi of n in square brackets. Okay, so in other words, this the average case number of comparisons or average number of comparisons is 1 by factorial into the summation sum over all permutations, the number of comparisons required for that permutation for quicksort. Okay, in other words, it's nothing but the expectation or the expected number of comparisons when the array is chosen uniformly at random. That is, you permute or you randomly permute 1 to n and then run the algorithm on that. Okay. So yeah, so this was the statement that we had seen in the last lecture. So one last connection was missing for completeness. That was connection to randomized quicksort. I had started off connecting, but it was not complete. Okay. Yeah. So let's just redo this analysis. I did, I think, in the last lecture itself, but I'll quickly go over that. Okay. So let's consider that our array is a random permutation. Okay. And our at the first level of regression, our primary focus is the first element. Okay. Now remember that the array is a random permutation of 1 to n. Yeah. So the first element is any of this, right? So what is the probability that a of 1 is I? So this is, in the denominator we have total number of permutations. In the numerator, the number of permutations which contain the first element as I. There are exactly n minus 1 factorial many such permutations. So this is n minus 1 factorial over n factorial, which is 1 by n. And this argument is, or this probability is independent of I. It's the same for every I. Or in other words, the first element of the array is uniformly distributed. Okay. So pause for a moment and let's think of randomized quicksort. So let's think of randomized quicksort on 1 to n. Sorry. Okay. So suppose the array consists of 1 to n. Let's also imagine that they're in that order. Okay. Then you can say, oh, what is the point in sorting and so on. Yes, there is no point in sorting, but we are just analyzing. Okay. This also works for any permutation of 1 to n. Now choosing a random pivot, what does it mean? Choosing one of 1 to n uniformly at random, right? Yeah. So probability that pivot is going to be I is 1 by n. So probability that pivot is equal to I is 1 by n. Okay. So when you feed the deterministic quicksort a random permutation of 1 to n, the effect of it choosing the first element of pivot is the same as randomized quicksort choosing the first pivot uniformly at random. The interesting part is it is irrespective of how the array is. See, for randomized quicksort, for any array it is the same. Okay, what I mean is any permutation of 1 to n, it is the same effect because it's uniformly picking an element. So it's irrelevant how they are ordered. Okay. So the first step of the quicksort and the first step of the deterministic first step of the deterministic quicksort on a random permutation and the first step of the randomized quicksort, they are essentially the same. They are doing the same thing, right? Randomly picking an element. Okay, so is it clear? The first step of randomized quicksort is the same as first step of deterministic quicksort, provided a random array or random permutation of 1 to n, to be precise. Okay, so now let's look at the subsequent levels. Okay, so this is, sorry, let's say this is L and this is R. Okay, now once you fix the first
Sir, can you
element,
repeat the equivalence between the two statements?
yeah, so the first step of the randomized quicksort, which is basically randomly choosing a pivot, right? Essentially like randomly choosing one of 1 to n as a pivot, right? Is equivalent to the first step of our deterministic quicksort, which is provided with a random permutation. When it is provided with the random permutation, whereas the first case of a randomized quicksort, we are providing a fixed permutation. In fact, it holds for any permutation.
Okay, so okay, good.
Yeah. Okay, so the probability process is equivalent. That's what I'm saying. What I meant to say is like get a random permutation and feed it to our deterministic quicksort. Look at the pivot, make the observation on the pivot. It's a random variable now, right? It's a random variable. It is the same as the random variable for randomized quicksort on 1 to n. Okay, that is the first pivot chosen by randomized quicksort on 1 to n. That is a statement.
Oh,
Okay, yeah. So, or in other words, the first level of recursion, they both behave similarly. Pretty much the same. It's the same random process. Okay. Now, for the second level, so let's consider the arrays L and R. Okay, so L is those elements less than the pivot, and R those greater than the pivot. Okay. So now we need one condition. Okay. So the condition is, so this left of array, so remember that as a whole we had a random permutation. Now elements which are smaller than I, so if you consider in the order given in the array, so they are again random. That's again random permutation of those elements. Okay, so we need the following statement. So once I chosen, that is first element chosen, the arrays L and R still random permutations. That is, L is a random permutation of its elements. Similarly is R. L or R, both are random permutations of. Okay. Yeah, so this fact I'm not really going to prove. This requires a bit better understanding of random permutations, property of permutations, also then conditional probability. You can just imagine the way process of choosing a permutation. You first fix the first element, chosen uniformly at random. Okay, and then see what you do is you change the process slightly. I'll have to prove that it's equivalent. I'm not going to prove it. I'm just giving it for intuitive understanding. Okay, you choose all this, you group all those elements which are smaller than and greater than, and you permute them. Okay, which is not equivalent, but the effect is something similar to you choosing a random permutation of the remaining. In fact, choosing the random permutation of the remaining is a bigger process. Okay, see what we are doing is you first fix the first element and then permute the remaining elements, right? This effect, if you now restrict. So let's imagine I'm having a lens. Okay, so two lenses, one is L and one is R. The first lens is I'm only looking for elements which are less than I and looking their relative position. So when I'm permuting the remaining n minus 1 elements, the elements I see from this lens, right, they are also permuting randomly, right? They are getting permuted randomly, right? Because the whole set is being permuted. So I'm also permuting this. So the effect is, what I have is for the left of the elements, I'm actually getting a random permutation. And similarly for the right of the pivot, I'm actually getting a permutation. See, all of these elements are, they're together going to be permuted. Now I'm putting lens on. You can just say that I'm coloring all elements less than I as red and coloring all elements greater than I as green. Okay. So now if you just observe the red elements, they are also getting permuted randomly, right? Do I make sense?
Sir, can I ask
Yeah.
one question?
Yes.
Here, before the first level of that permutation, this actual algorithm, you are providing with a random permutation. Okay, so
Yes. Yes.
that is, can I think like this analogy? Like you are before giving to the algorithm, like you have a deck of cards and you are shuffling, and that you are giving. Okay,
Yes.
so
Yes.
after shuffling, we don't know the outcome because it's a random process of
Yes.
shuffling. And
Yes.
then after the first level of that iteration is over, you will get that L and R. You are again independently shuffling that. You remove that ith element, like that
No.
first element.
I'm not shuffling them. So that's the difference. See, the only observation I made was the first element. Okay.
Okay. Okay.
So L is what? So I'm just not moving elements in L around. Okay. So I'm just marking them as elements which are less than the pivot. Okay.
Yeah. Yeah.
Now in the original shuffling itself, if you have the effect of the original shuffling,
Hmm.
okay, so
Yes.
these elements in L, they still look random. They're still random, right?
Okay.
That
Okay.
randomness is not lost because I'm not reordering elements in L. I'm just marking them. See, when I say left subarray, right, I'm only marking them essentially. If at
Okay.
all I'm moving to a subarray, a new array, but I'm not going to change their positions. Their relative positions are the same in relation to each other. So you can just so maybe I'll just okay. So ignore this text here. Okay, I'm going to draw something here. Okay. So okay. So this is my first position. Let's say this is my L and this is my R. Okay. So let's not mark LR. Okay. So that it's not confusing. Okay. So what I do is, so for left, I'm going to mark it as red. Okay. For right, I'm going to mark as green. Okay. Remember that the original permutation was random, right? Now if I'm looking at only the red ones, how will they look like?
Yeah, they will be in random positions.
They will be still in random order, right?
Yeah.
Yeah, everyone else agree? See, originally I had random order. Only observation I made was the first element, and then based on first element, I just marked them. I didn't move them around. I didn't touch them. I just observed. That's all. Okay, these are less than. These are greater than. So if I just look at, this is my L, right? Those marked red, they are still in random order. Similarly, if I look at green, they are still in random order. Their order did not change.
So you're
See,
saying they're as good as they were before,
exactly.
and
Because
hence
my
they're random.
only observation, only thing I determine now is the first element. I know what is it. So that randomness is gone. Everything else, it is intact. Okay, so that is an intuitive explanation. Like I said, I mean, mathematically, we'll have a lot of work arguing it. We'll skip it. Okay, so we'll not get into it. So, but I just want you to understand that the left subarray now again is a random permutation of its elements. Right subarray is again a random permutation of its elements. Okay. So that is all is required. So left subarray again is a random permutation, right subarray is random permutation. Now if I look at the first level of recursion, right, second level, so the pivots are these elements. As observables, they're again uniformly distributed among those in L, among those in R.
Sir,
But that's
can we
fine.
think of
Yeah.
this way? So
Yeah.
when you say L and R are still random, if we
Yeah.
consider the elements of L only L,
Uh-huh.
and so can we think like this? The chance of getting the whole permuted array is the same as if the chance of getting only the elements of L when they are like the permutation in the entire array. The chance of getting the permutation in the entire array is same as the getting the permutation in L. Like if you pick only the elements of L, the chance of getting the permutation which is there in the elements of L in this array.
Yeah, same as their relative position in the original array. Yes, their
Yes.
relative position. See, the point is, see, there is one thing that we need to note is elements of L are fixed for us now. Okay.
Okay.
See, once I fix I, so once I fix the first pivot, elements of L are fixed. It's only about, when I say random, it's their relative position. That is their ordering. See, if I just look at this as a relative, see, though this is the first element, this is the second element, this is the third, this is the fourth element, right? This relative positioning, say if I is 10, then this should be elements from 1 to 9, right? The elements are fixed, but their relative position is not fixed. It is random. So their relative order. So if you just, so if I scan the array from left to right and look at their order. So this is the first element, this is the second, say this is 3, this is 7, this is 6, this is 4. Okay. So 8 is the pivot, let's say. So then this positioning, this permutation, that is random. That is all we are saying. It's the same as their relative ordering in the original permutation. Yes.
So okay, it's the words of saying as good as before.
Yes, as good as before. Yeah. Okay. So in other words, so when I choose pivot in the second level of recursion, say for L, okay, so the first element is random among all candidate elements. That is 1 to I minus 1 in our example. I mean, in our case, because we are considering permutation of 1 to n minus 1, 1 to n. Okay. So this is 1 among all. So it's in effect choosing the first element under a random permutation fed at the input is the same as the second level of recursion for quicksort, randomized quicksort. It is permuting the elements uniformly at random, or in other words, I mean, what it does is it basically pivots, chooses a pivot uniformly at random, right? So it's the same effect as feeding our quicksort with the permutation, random permutation, and choosing the first element. Similarly, for the next level, the corresponding level of recursion for R. And in the subsequent, once you fix this pivot, now again you have you will subdivide this into left and R, right? So L, R, this again L and R. So again, if you choose pivot here, it will have the same effect here. Oh, sorry. Okay. If you choose pivot here, it has the same effect. Okay. So, or in other words, at subsequent levels of recursion, still the corresponding elements are randomly positioned, or they are random permutations. Okay. So hence choosing the first element as a pivot is equivalent to choosing an element in the range uniformly at random as a pivot. When I say in the range, within L or within R, whatever. Okay. So, or in other words, at level by level, our deterministic algorithm, when fed with the random permutation, the behavior is similar to randomized quicksort. Okay. So, like I said, I mean, we didn't really prove that elements in L will be randomly permuted and randomly elements in R are randomly permuted. We just take it for granted. I hope I mean, intuitively you feel for it, right?
Yes, sir.
Yeah. So particularly with this example, right? I mean, if these are randomly positioned, when I color some elements and look at their relative position, they are again randomly positioned. That is all. Okay. So, yeah. Okay, so that is all the connection between average case analysis of quicksort and randomized quicksort. So in other words, so in the first level of recursion, any of 1 to n being the first element is equally likely, or in other words, it's equivalent to choosing a random pivot. Okay, so the quicksort above with the random array is the same as randomized quicksort with respect to expected behavior or with respect to any other probability statement that we make. See, you can just imagine a randomized algorithm is a random experiment. Okay, you're observing some outcomes, maybe the number of comparisons or running time, I mean, equivalently running time or any other properties. Okay. Similarly, a deterministic quicksort with a random permutation is also a random experiment. Okay. So from our observation, as random experiments, they're essentially the same. What do you mean by essentially the same? If you look at the distribution of pivots in the first, that is the random quicksort, okay, you are randomly choosing. I mean, at each recursion level, you are randomly choosing a pivot, right? So you look at the distribution. The first pivot is this, second pivot is this, third pivot is this, and so on. Similarly, you look at the distribution of pivots in the second experiment. That is, at the deterministic quicksort that we have described, which chooses the first element of the array as a pivot, and run it with a random array or random permutation. The distribution is the same. Okay, they're similarly distributed. Or in other words, if somebody comes and looks at these two random variables, they are essentially the same. They are indistinguishable. Okay, so that way, behaviorally, both are essentially the same, though both are saying different things. Okay, the first one is saying, I mean, when I say first one, the randomized quicksort, it's actually having a fixed input, and it is choosing the pivots randomly, whereas the second algorithm, it is not having a fixed input, it's having a random input. Okay, so the analysis wise, they are in a way, I mean,
Excuse me,
from
sir. Sir,
performance view, yeah.
What do you mean
Yeah.
by fixed input?
So for deterministic quicksort, we are analyzing with respect to fixed input, right? And we are taking the maximum among all those inputs. Sorry, randomized quicksort. Sorry, randomized quicksort.
You take a input. I'm not understanding what is the difference between. I understood what is randomly picking up an input, but random permutation of an input. But I'm not understanding what is a fixed input.
So how do you analyze quicksort? So you look at running time, take maximum over all possible arrays of length n, right?
Yes.
That is what our analysis.
Yes. Yes.
So when you analyze, input is fixed for you, right?
Okay.
When I say fixed, I mean it's not fixed, but arbitrary fixed input. When I say, I mean, when you, so there is no distribution on the input, it's deterministic, right? Or you can imagine adversary is choosing. So you can imagine the input is as bad as possible. Whereas in average case analysis, you don't make any assumption on the input. Input is random, that is uniformly distributed among possible inputs.
Okay. Okay. I understood now. Thanks.
Yeah. But the effect is the same in the sense that the way randomized quicksort chooses permutation, it's actually doing an average case over all permutations, in effect, because you look at the distribution of the pivots, they are the same in both the cases. So that way the effect happens to be the same. Or in other words, for us, life is simple. Okay, we just get the following theorem. The average number of comparisons performed by quicksort on arrays of length n is order of n log n. In fact, 2n log n, right? 2n log to the base of e, log n to the base of e. So that is all. In other way, I mean, what I mean to say is, like, in general, doing average case analysis is extremely tedious. Okay, in many algorithms or many problems, yeah, like I said, I think there might be some 10 to 15 algorithms where complete average case analysis is known. Otherwise, no tight average case analysis is known. Okay. Whereas randomized algorithms, I mean, yeah, there are a lot, plenty of randomized algorithms where the analysis is known. So that way, I mean, this observation actually led to, in one shot, we got the performance analysis of average case, average case analysis of quicksort itself right away, okay, using randomized quicksort. Yeah. Okay, so I have 1 or 2 minutes to take questions. Yeah.
Hello, sir. Am I audible?
Yes, you're audible. Yeah.
Sir, in case of means when deterministic quick sort, and there that time we are choosing the pivot element means pivot element, we are choosing always the first one or something that is fixed, whatever we are choosing.
Yes.
And
You're right. Yeah.
but in the case of randomized quick sort, array is fixed, but the pivot where I will choose whether the first position or second position or third position, that is not fixed.
Yes. So when I say array is fixed, I mean you can imagine array is given by the adversary. So the worst possible array is given to you.
That is randomized. And in the case of deterministic quick sort, array itself is random.
Yeah, for average case analysis, yes. See, for average case analysis, the deterministic quick sort, array is permuted, whereas the pivot is fixed. I mean, the position of the pivot is fixed, the first element in the array.
And so then in case of randomized quick sort, there will be no meaning of worst case, average case, or best case analysis. No, everything will be same only, no?
No. It's the worst case analysis. So that's what, right? So we are looking at expected performance, the worst case. So that's what I said, right? When the input is fixed, there is an adversary sitting in front of you who is going to give you the bad possible, worst possible input. That is the imagination.
Okay.
Okay. Yeah.
Okay. Thank you.
Yeah.
Sir,
Yes. Yeah, please go ahead.
sir, like you said, adversary will be giving as bad as possible. So that bad means bad kind of thing.
Yeah,
That
so I mean, it's our imagination.
you are
Okay,
saying for fixed.
Yeah, whenever possible, we take the worst possible. That's all. Hello, I think there is a break.
Yes, sir.
So can everybody hear me? I could not hear you. A couple of words I could not hear.
Sir.
Yeah, can you repeat the question?
So what I
Hello?
mean to say, you said about that fixed. Sir, a fixed input you said, right?
Yes.
So
yes.
you said an adversary can give as bad as possible input. So what I mean to say, so he can give the most bad kind of thing. So that is why it's fixed.
Yeah.
It's not a random thing he is giving.
Exactly. So see, when I say fixed, it is deterministic. That is all. Okay. Yeah, it's not like, okay, I just fix this array and analysis. No. So when I say fixed, it is as bad as possible, but deterministic. So during the, I mean, there is no distribution.
Yeah.
That's all. Yeah.
Okay.
Okay. Yeah.
So, sir, in the randomized quick sort, even if the adversary gives us the worst input, we are choosing the pivot in random. So even if adversary gives the best input also, then also we are choosing pivot randomly.
Yeah, that's a very good observation. Okay, so in effect, what randomized quick sort does is like it randomly permutes the input, or in other words, see, for every input, randomized quick sorts performance will be equivalent to the average case performance because it's taking average over all permutations. See, when you say expectation, right? Expectation is nothing but average. So expectation over the choice of pivots. So, but choice of pivots is nothing but a permutation, right? It's basically a permutation of the input. So the randomized quicksort, in a sense, what it does is irrespective of its input, it basically randomly permutes the input. Okay.
Yes, sir. It means whatever be the input, may it be reverse sorted or nothing. I mean, anything. Always the time taken will be unlocked.
Exactly. So expected time. Okay. So expectation. So yeah.
Yes. Expected time.
Yeah. So that's also one more observation I wanted to make. So one easy way to understand is if you just look at the trail of the pivots chosen, right? by randomized quicksort. Okay, so let me spend 1 or 2 minutes on it. Okay, let's see where is okay, so let's look at the pivots chosen by quicksort. Okay, pivot 1, pivot 2, pivot 3, etc., by the randomized quicksort.
Excuse me, sir.
Yes. Yeah.
Sir, in deterministic quicksort, if adversary gives us uh, a input and we randomly permute it, so and permutation turns out to be sorted order, and we choose the first object, and then the right side becomes itself sorted. Then we choose the second element of first element of the right side. Then itself the right side will become sorted. So sir, in this case, the complexity will turn out to be n square.
Yeah, but what is the probability of that happening? See, that is what, right? When we say expectation,
Of
we don't
choosing first element.
exactly. So when you say expectation is n log n, that means with a good probability, it's going to be n log n. But there is also a non-trivial probability that it could be n square. Yes, there is a non-zero probability that it could be n square. Yes. So either this sorted order or sorted in the opposite order or almost sorted order, those are also bad, right? So all those, there is still, see, it's not saying that there is zero probability of that happening. No, there is a non-zero probability, but the good probability is on the good side. That is n log n. That is all. Is that clear? Does that clear the question?
Sir, I'm talking about.
Huh.
Sir, I'm talking about deterministic quicksort where we don't.
No, deterministic. So we only considered average case analysis, right? So on an average.
Randomized
So if you average over all inputs, this is what. But still, there could be bad inputs, right? Where the running time is as bad as possible. There are, but there aren't many. That is all. When I say average case is this, that means roughly for half of the inputs, it's going to be this. Beyond that, they could be higher. Yes, there are bad inputs, of course.
Talking about average case, we do not consider sorted arrays. That random permutation is a
No. We
sorted
can see
array.
when we take average over all arrays, right? Sorted arrays are also included in the average. All possible arrays are included in the average. You just sum it up and divide by the number of inputs. That's all.
Okay, sir. Okay.
Yeah.
Thank you.
Yeah. Okay, so I'll spend a couple of minutes on this. I mean, it's probably it will make it feel a bit better about the view of randomized quicksort versus average case. So let's take, sorry, let's run the randomized quicksort and take the trail of these pivots. Okay, first pivot, second pivot, and so on. So write the array in that order. Okay. Is that clear what I said? So you just look at each recursion level of randomized quicksort. So this is the first level. At the second level, there are two arrays. So P2 and P3 and so on. You just write them as an array. What will this be?
The random permutation that was given as input to the deterministic quicksort.
Yeah, so let's ignore deterministic quicksort. I mean, if you just look at the array, so the array is given deterministically, but the algorithm permutes it. So our algorithm chooses a pivot uniformly at random. So then this basically looks like a random permutation of the input array, right?
Yes.
That is all. So the trail of the pivots, so the choice of the pivots essentially defines a permutation. Okay. So in the case of average case analysis, all we did was this was done a priori at the input. That's all. So for randomized quicksort, if you look at the trail of the pivots, it's basically a permutation. It's basically a permutation of the input. Okay. So that permutation we are choosing randomly at the input itself. Now the deterministic version does not, it only observes a fixed location as a pivot. That is all. Okay, so both essentially are permuting. One is permuting at the input, the other one is permuting along with the algorithm. That's all. Both are permuting one to n. That is all. Okay, so both the algorithms are essentially doing a permutation. One does during the course of the algorithm, but then what is the input? Input, I said deterministic. So, but this holds for any input. So for any permutation, it does a random permutation. Whereas here, you assume that at the input you have a random permutation, but the algorithm is deterministic, or that locations of the pivot is fixed, kind of course, based on the input, but it is deterministic. Okay, so yeah, that way essentially both algorithms are essentially the same. Okay? What I mean is essentially the same with respect to their overall behavior. But for practical purposes, deterministic algorithm is deterministic. It does not use any randomness. Randomized algorithm uses random bits. Yeah. Okay. So shall I move ahead? There are no questions. Okay. So today we are going to look at another related problem. Some of you might have seen it already. So we call it as median finding. We are given an unsorted array A, say of n elements. Okay. So we need to output the middle element, or in other words, element of rank n by 2. When I say middle element, not middle element in the array, but which is in the middle of the sorted array. Okay. So model is the usual comparison model. Okay. So one thing is, see, it's the same with sorting also. Okay. So see, if the algorithm knows that input is 1 to n, right, is a permutation of 1 to n, do we require n log n comparisons?
No.
No, right? You just output 1 to n, that's it, right? What is the big deal? You know the sorted order. Okay. So the reason why we could do analysis on 1 to n was the algorithm was not knowing what the input domain is. It was only comparing two elements. It's capable of comparing two elements, nothing else. Okay. So in other words, so the effect was the same. See, it does not matter what domain you choose the input from. You can always imagine that you are choosing from 1 to n. Okay. So similarly for this, again, we are considering comparison model. Given that the algorithm does not know what the values are, we can always imagine that our array is from 1 to n, if it helps. Okay. Okay. So what is the straightforward algorithm? What will be your first solution?
Sort the
Sort and
elements.
output the middle.
Okay. So first solution, sort the array, output the middle element, right? Okay. So let me state a more general version of this problem. Okay. Where instead of n by 2, you have k. So we call it as k selection. Okay. So if k is 1 or 2, it is easy to do. K is 1 means it's a minimum element. K is 2 means the second minimum element, or k is n means maximum element, and so on, right? But for other values of k, say k is 3n by 4 or n by 4 and so on. Here again, the trivial solution seems to be this, right? You sort the array and output the kth element. So in general, kth element, k selection. Okay. Yeah. So this problem, people had studied since the 1950s itself, okay, or maybe 60s. So initial years, people thought there is no better solution than sorting. Okay. So until the early 70s, people believed that, okay, they should be able to prove a lower bound of sorting, that is n log n. See, at the outset, right, you don't see any better solution, right? How are you going to do it? You just look at the problem, there is no clear solution as such. sorting seems to be the only solution, but sorting requires n log n comparisons. So now the question is, can you do better? So in the late 60s and early 70s, people believed that, okay, there is no better solution. So I think it was in 1972. I don't remember the researcher's name. So people came up with randomized algorithm, which runs in expectation linear time. Okay. Soon after that, I think in 2 or 3 years, people also came up with the deterministic linear time algorithms. In fact, one of them is called median of medians. So yeah, so we'll present this randomized algorithm, which is basically quicksort, okay? Quicksort with some tweaks. And then we'll also see deterministic solution probably in the next lecture, okay? Yeah, so without much wait, I'll just present the algorithm right away. Okay, so like I said, it's essentially quicksort. We call it as quick select. So that is what probably you would have also imagined. I mean, you just look at quicksort. Now, instead of sorting, you just do the corresponding search or the select algorithm or median finding algorithm. Okay. So let's assume input is an array and we are given k. So the algorithm is for k selection instead of median finding. But this also works if you just run the algorithm with k as n by 2 or ceil of n by 2 if n is not even. It has the same effect, right? I mean, it gives you the median. Okay. So what you do is you randomly choose a pivot. Okay. Now partition the array into 3 parts as usual. The left, those less than the pivot, middle equal to the pivot, right greater than the pivot. Okay. So okay, so let me, for reference, let's just draw it here. Okay. So this is my pivot. Let's say this is pivot A. This is less, this is greater. Okay. Okay, so now let's look, do a size analysis of LR. So what if size of L is k minus 1? What do we know?
A is the median.
So if L is k minus 1, there are exactly k minus 1 elements less than A. So the rank k element must be A, right?
Yes, sir.
Yeah, do you all agree?
Yes, sir.
Yeah, so the kth smallest element must be A. So that's all we do. So you just check if size of L is k minus 1, then output A. If size of L is greater than k, what does it mean?
Median lies in L.
Yeah, so the rank k element must be in L, right? So we recursively call quick select L, the rank remains the same, k, and size of L. Okay, so this parameter is actually not necessary, but anyway, let's keep it for brevity or ease of understanding. Okay, so you just recursively call quick select on the left hand side. So the third possibility, only possibility, is L less than k minus 1. So this else implies cardinality of L is less than k minus 1. In that case, our rank k element should be in R, right? That's all we do. So we run quick select. Now what should be the rank of that particular element? So the element of rank k in the original array A will be of what rank in R? So we are removing cardinality of L plus 1 many elements which are smaller than that element, right? Surely. See, this third case also means our rank k element is bigger than pivot, right? So this statement you can just say rank k element is equal to pivot, rank k element less than pivot, rank k element greater than pivot. So when it is greater than pivot, I'm removing exactly these many, that is cardinality of L plus 1 many elements which are smaller than the rank k element. So what is the effective rank of that element that we are targeting in the new array? I'll shave off those values from k. So k minus size of L minus 1. This is for pivot. Okay. So we recursively call pick select R k minus cardinality of L minus 1, and the size of new array is R, cardinality of R. Yeah. So this is it. This is our algorithm. So first thing is, is the correctness clear from these three cases?
Yes, sir.
Yeah. So to everybody, is the algorithm clear to everyone?
Yes, sir.
Yes, sir.
Yes,
Okay.
sir.
Okay. Good. So let's say correctness. So the first observation is observation 1. I'll just write it a bit formally. Okay.
Sir, why,
Yeah.
excuse me, sir.
Yes.
Sir, in the previous slide, why did you take k minus L minus 1? Just remove this left part only. Because
Yeah,
k
I'm
is
also
the
removing A, right? So I'm also removing A.
No, only L minus 1 elements. Why k minus L minus, mod L minus 1?
Ah, that's a good point. Okay. See, we are talking about rank, right? So in the overall array, I want the kth smallest element. That is element of rank k, right?
Yes, sir.
Yeah. Now, when I consider R from the original array, I have removed cardinality of L plus 1, this pivot, many elements which are less than this rank k element, right?
So
See, in the sorted,
we already decided that the rank k element which we want will be on the right side of the pivot that was generated first time.
yes, you're right.
So why not remove all these left elements and take elements from the right side of this pivot, or allow pivot to the rightmost side?
No, I didn't get your point. So what is it you're saying?
I am saying that suppose that A is a pivot element that we got first time when we run this algorithm, and
Hello. Hello.
Sir, you are audible, but I guess she's not.
I'm audible. So I think she dropped out.
Yes.
Okay, so we'll wait. Was it Shivani?
Yes, sir.
Okay. Okay.
Excuse me, sir.
Yes. Yeah.
Sir, can we simply say this? It is when we have when we do the fifth step, it is k minus rank of pivot.
Yes, that's right.
Okay.
Yes. Yeah.
Sir, I think Shivani was saying that in fifth line, we are passing the argument k minus cardinality of L minus 1. It should be k because we are changing the element. I mean, her question, I think that her question was that we are changing the k here.
Yeah. Yeah. So let's wait for a minute. I mean, for her to join.
Yes, sir. Yes, sir.
So yeah, I think she dropped out. Let's. Yeah, I felt she was saying the other way around. I mean, I thought, why don't you remove those elements on the right hand side? So that's what I got confused. So yeah, let's wait. Okay, any other question here?
So in general words, can we say that the second argument in quick select, hello, is
Yes,
the relative
yes.
position of the kth rank element with respect to the pivot?
Yeah, No, with respect to the pivot.
No, I'm not saying
That
the pivot is the origin here.
okay, okay.
Suppose if the
No, only in
pivot,
the fifth case it is true. Otherwise, it just stays as it is, right?
it
I
stays as it
mean,
is. Yes.
step 4 there is no change. Step 5, yes. Step 5 basically you shave off pivot many elements. I mean, rank of
Okay.
pivot
Okay.
many elements.
Understood now.
That is all.
Understood now.
Yeah,
Thanks.
yeah. Okay. If she's not back, let me just explain it. Okay. So anyway, it's in record, right? So she can see it later. Okay. So
My connection was lost. Sir, you continue.
are you back? Okay.
Yes, sir.
Okay. So yeah, can you quickly repeat your question? So this so you were saying it should be K, right? Is that right?
No, sir. I am saying when I ran this algorithm first time, I got this A, and this was not the desired with the smallest element. So I checked this condition. Third, it was wrong. Fourth, it was wrong. Then we went to the fifth condition. It means that
Fifth,
the
yes.
kth smallest element lie on the right side.
Yes. Yeah.
So we will not need any of these left side elements.
Yes.
So why not take from the after like along A element to the rightmost element only? Why this K minus model minus 1?
No. So K minus 1 is the effective rank. Okay. So see, what is my new array? New array is this portion, right? R.
Yes, sir.
Okay. Now what is the rank? So see, my rank K element was sitting here. Okay. Now it is sitting here. Say, let me use a different color. So it is here. Okay. This is my kth
Yes, sir.
element. So in the overall array, its position was K. Okay. Now in the new array, what is its position? In the new array, its
Yes.
position is this, right? Whatever is
Yes,
to
sir.
the smaller than that. So what is that? So I know that for sure, compared to this element, exactly cardinality of L plus 1. That is the rank of pivot. Many elements are dropped off, which are less than this element, right?
Yes, sir.
So hence the effective rank of my rank K element in the new array will be K minus whatever is being thrown out. See, I'm only
Okay.
looking at this array now, right? In this array, what was rank? Its rank is only this much, right? What is
Yes,
this
sir.
value? This value is K minus this much, which is cardinality of L plus 1, which is basically K minus cardinality of L minus 1. And this is K minus cardinality of L plus 1, so the minus comes here.
Okay, sir. Yes, sir. Got it.
Got it, right?
Yes, sir.
That is all. That's all we are doing. Okay. Yeah.
Yes, sir. Thank you, sir.
Yeah. Good. Yeah. Okay. So correctness is kind of clear. I'll just write down formally in the next lecture, and we'll do the comparison, number of comparison analysis also in the next lecture. It's basically a restricted version of analysis of quicksort. Okay. Yeah. So if you have any question, please drop me an email. Else we'll meet tomorrow. Okay. We'll stop here.
Sir,
Srinivasa, you can stop the recording. Yeah.
sir, Piyush has a question, sir. In the chat, it's there in the
Okay.
chat.
Sorry, I didn't see it. Okay. Yeah, so I'll read out the question. I want to ask whether these live lectures are compulsory to attend. Yeah, so if you have network issues, please drop me an email. Okay, so those who have network issues, I'll just keep note of it. Otherwise, the lectures are compulsory. So I want so if people who are facing trouble should be sending me an email. Okay, yeah, we'll see how to resolve it.